By the time of the SLAC MIT experiment, scientists already had some ideas about how the proton and other subatomic particles, similar to the proton, are built. All discovered subatomic particles have quite similar properties, that is, they have a difference only in a few internal or intrinsic characteristics. Each particle has a number of such internal properties, or quantum numbers, which uniquely characterize them and are related with the corresponding interactions. For example, the electric charge is one of such characteristic, which appear under interaction with other charged particles, on with an electric and magnetic fields. The electric charge is measured in the units of the charge of electron. It should be discrete as all other quantum numbers. Another important example is the intrinsic form of angular momentum of a particle, which called a spin of particle. As the name suggests, spin was originally conceived as the rotation of a particle around some axis that is related with its magnetic properties. So, we can imagine the particle as sphere and spin as its own rotation. However, really, the particle is not the sphere and spin is a solely quantum mechanical phenomenon. It does not have a counterpart in a classical mechanics, so cannot be interpreted classically or in our usual point of view. The Stern-Gerlach experiment are usually used to demonstrate that electrons and atoms have an intrinsic angular momentum or spin. This experiment involves sending a beam of particles through an inhomogeneous magnetic field and observing their deflection. The result of experiment was rather unexpected. The particles passing through the Stern-Gerlach apparatus are deflected either up or down by a specific amount, while they expected the random and continuous distribution. Let's imagine a particle with spin as a sphere with two magnetic poles, red for south and blue for north. Spin of particle interacts with the external magnetic field. If spin may have any value, then a deviation of particles under the action of the external magnetic field will arbitrary. The Stern-Gerlach experiment showed that spin can have only two values along the external magnetic field, in the same direction or in the opposite direction, which correspond to spin up and spin down, or, more precisely, a projection of the spin on the direction of the external magnetic field. The results of experiment showed that particles possess an intrinsic angular momentum that is closely analogous to the angular momentum of a classically spinning object, but that takes only certain quantized values. Spin of a particle is measured in the units of the spin of photon. It should be discrete, but such particle as electron, proton, neutron have the spin equal to half of unity. We have two particles with the spin half of unity which can imagine as a top toy in the form of a half sphere. Suppose these two particles are identically, that is, they have the same internal properties or quantum numbers. We want to put them in the same place, for example, inside the sphere. There is some fundamental principle of nature, which usually called the Pauli exclusion principle, stating that no two particles with the spin half of unity can share the same quantum state at the same time. In our demonstrative example, this means that we cannot put in the same place, inside the sphere, two identical half-sphere. However, we can do this, if we flip vertically one of half-sphere. In this case our state will not have the same internal properties or quantum numbers. They will differ in the direction of the spin, or, more accurate, the projection of the spin. One half-sphere will correspond to the spin up, while other will correspond to the spin down. If we take a different particle, it will not feel these particles and it can share place with any of these particles. This procedure is nothing as the construction of the proton and other subatomic particles from an elementary particles, which was proposed by Gell-Mann and Zweig in 1964. According to their idea, the proton, neutron and other similar particles with half-integer spin, 1/2, 3/2 and so on, called baryons, consist of three elementary particles. Particles with integer spin, 0, 1 and so on, called mesons, consist of two elementary particles. So, that problem was the following: think out an elementary particles with some internal properties, which can be used to construct all known particles. They introduced only three particles, which was called quarks by Gell-Mann, and constructed all known at that moment particles, not only baryons, but also mesons. How this works? Let's start with our usual particles proton and neutron. Neutron has charge 0, proton has charge +1. Both particles have spin half of unity. So, Gell-Mann and Zweig construct these particles from two type of quarks, U and D. All quarks have spin half of unity, and to obtain the same spin for proton or neutron we should take one quarks with spin down. In this case total spin will half of unity. It is easy to calculate what electric charge should have U and D quarks. They have charge +2 divided by 3 and -1 divided by 3 in unity of the charge of electron. The charge of quark is fractional. To construct all other known baryons with half of unity spin, they introduced an additional quark, S quark. It has the same electric charge as D quark. The construction of all particles is really a mathematical game. You should put all particles on the array. Each line in the array respect to a number of the corresponding quarks. For example, the horizontal lines correspond to a different numbers of S quark, 2 S quarks, 1 S quark and 0 S quarks. An intersection point of the lines of array corresponds to some baryon, if exactly 3 quarks are situated in this point. So, we should consider a hexagon. All particles, which can be constructed in this way, were already known. Moreover, it is possible to find some relation between the masses of the different particles in the array, what were done by Gell-Mann. Mathematically, it is possible to do the same for the baryons with the 3/2 of unity spin. We should extend the array to include the lines with 3 quarks. In this case all quarks will have the same direction of their spins, and according to the mathematical theory, we can construct the following states, or baryons. What is the most intriguing? That Gell-Mann predict new particle from his completely theoretical consideration. This particle was indeed discovered with some upcoming experiment. So, this model was very pretty, but had some unusual features. First of all, the fractional charge. Nobody did find the fractional charge in any direct experiment. Second problem was related with the Pauli exclusion principle. The particle, which was predicted by Gell-Mann and discovered experimentally, should consist of 3 identical quarks. In any case 2 quarks will have the same quantum numbers, what is in a contradiction with the Pauli exclusion principle. To resolve this problem, Greenberg suggested to introduce a new, earlier unknown, internal property, or quantum number, for quarks, which was called color. As well known, all variety of colors around us may be obtained from the three primary colors, red, green and blue, mixing in the different proportions. Taking all three colors in the same proportion, we get a white color. So, each of the three quarks inside the proton, or baryon, has one from the three primary colors. Together they give a colorless proton, or baryon. Electrically charged particles may have positive or negative charges. For example, electron has the negative electric charge, while its antiparticle, positron, has the positive electric charge. Quark may have the color charges, red, green or blue. Antiquark, which has the opposite electric charge, may have the anticolor charges, anti-red, anti-green or anti-blue, which are really cyan, magenta and yellow. D quark and 2U quarks with red, green and blue colors may combine into the proton, which is colorless with the electrical charge +1. Anti-D quark and 2 anti-U quarks with cyan, magenta and yellow colors may combine into the antiproton, which is colorless with the electrical charge -1. At the moment we know that there are 6 different types of quarks. Fourth type of quark is C quark, or so-called charm quark, and its antiquark. Fifth type of quark is B quark, or so-called bottom or beauty quark, and its antiquark. Sixth type of quark is T quark, or so-called top or truth quark, and its antiquark. Masses of every new type of quark are much more of all previous quarks. The fact that these three colors indeed exist was confirmed experimentally by studying the processes of annihilation of electrons and positrons in the accelerators. Since the positron is the antiparticle of the electron, then in according with the quantum field theory, they will annihilate under a collision and will produce another particle-antiparticle pair. This new pair may be any pair within the energy of annihilating pair. So, we can produce an electron-positron pair, a quark-antiquark pair, and so on. The special detectors may identify a producing pair experimentally, while with the help of quantum field theory we can calculate the expected number of events depending on the type of the produced particles. The theoretical prediction can be obtained for the ratio of the cross-section of the pair of particles having a color to the number of particles, which don't have color, electron or very similar particle muon, which can be easily detected. The theoretical predictions depend on the sum of the square of the charges of quarks, which can be produced, and the number of colors. If we can produce first 3 type of quarks, U quark, D quark and S quark, we should expect that this ratio will be about 2, what is good agreement with experimental data. If the energy of annihilating pair will enough to produce a 4th quark, which called as charm or C quark, and its antiquark, the expected value of ratio will slightly less than experimental data. However, for this case large corrections should take into account. If the energy of annihilating pair will enough to produce a 5th quark, which called as beauty or B quark, and its antiquark, the expected value of ratio will in a nice agreement with experimental data. In electromagnetic interactions, electrically charged particles, such as electron and positron, exchange photons, the carriers of the electromagnetic force. Since the color is a fundamental property of elementary particles quarks, then this property must appear at some interaction with another object that has the same property. This interaction has been called the color interaction, and the theory that describes such interaction is called the quantum chromodynamics, by analogy with the theory of electromagnetism, the quantum electrodynamics. In color interactions, the quarks exchange gluons, the carriers of the color force. Gluons, like photons, are massless particles with a whole unit of intrinsic spin. However, unlike photons, which are not electrically charged and therefore do not feel the electromagnetic force, gluons carry color, which means that they do feel the strong force and can interact among themselves. Usually, the color force is called as a strong force. Strong force is one of the four fundamental interaction of nature that acts between subatomic particles of matter. At atomic scale, it is about 100 times stronger than electromagnetism, which in turn is orders of magnitude stronger than the weak force interaction and gravitation. Let's look at the color force closer. As we know, quarks carry three types of color charge: red, green and blue. Antiquarks carry three types of anticolor: cyan, magenta and yellow. Gluons carry both color and anticolors. There are 6 color-mixing gluons and 3 colorless gluons, as they carry color and its anticolor. Some of mixing gluons form gluon-antigluon pairs. According to quantum chromodynamics, 3 colorless gluons should combine into 2 states. So, there are the 8 gluons at all, which carry the color charge between quarks or gluons themselves. How this works? Let's look inside some baryon, for example proton, which consist of 3 quarks with different colors: red, green and blue. Green quarks may emit green-yellow gluon and becomes blue. Green-yellow gluon may be absorbed by blue quarks and it becomes green. There are a lot of such possibilities. Important, that at each moment the whole system quarks and gluons should be colorless. In principle, quark may emit colorless gluon. In this case quark will not change color. As colorless gluon is a superposition or a mixing state of all colorless gluons, it can convert to other colorless gluon. Such gluon will not change the color of quark, which absorbs its. Moreover, gluons may interact among themselves and may be transformed into a new gluons. One can easily extend this procedure to another possibilities. Take into account the different self-interactions of gluons. The strong force similar to a spring. In that as you stretch a spring, it gets harder and harder to stretch it more. When a spring is stretched beyond the elastic limit, it breaks to produce 2 springs. In the case of the quark pair, a new quark-antiquark pair will be created when pulled beyond certain distance. Part of the stretching energy goes into the creation of the new pair. As a consequence, one cannot have quarks as free particles. We can't see an isolated quark because the color force does not let them go, and the energy required to separate them produces quark-antiquark pairs long before they are far enough apart to observe separately. This phenomenon is known as color confinement. Quarks never appear in isolation,